Hello everyone, my name is Henrique Matsuoka and welcome to my presentation on singular homology theory and its applications. First, I would like to talk about algebraic topology in general. As its name suggests, algebraic topology connects topology and algebra. This is done by assigning algebraic structures such as groups or modules to a given topological space in such a way that those algebraic structures preserve certain characteristics of the topological space. One of the main objectives of this construction is to be able to compare topological spaces via those algebraic structures, which at times can be easier to work with than the structure of the spaces. In this way, we can say which characteristics certain spaces have in common, for instance, if they are homeomorphic, if they are homotopy equivalent, and so on. So let's start talking about the construction of the singular homology groups for a given space X. For this, at first, we must work with the concept of simplex, which will be the basis for the construction of the homology groups. A simplex is, in general terms, the generalization of the notion of a triangle to an arbitrary dimension n. Here in the slide, we have some examples of simplexes. The simplex of dimension 0, which is a point, dimension 1, which is a line, dimension 2, which is a flat triangle, dimension 3, a triangular pyramid, and so on. A n-dimensional simplex is defined as a set of n plus 1 vertices, and it is the smallest convex set of the Euclidean space Rm containing all those n plus 1 vertices. The n-simplex will be denoted by an ordering of the n plus 1 vertices for the sake of the construction of the homology. It is also important to emphasize that when removing any of the vertices of the ordering of an n-simplex, we will have an n minus 1 simplex, and that n minus 1 simplex will be what we'll call a face of the previous n-simplex. Here we have the formal definition for what will be a standard simplex of dimension n, which will be a simplex with the n plus 1 vertices being the unit vectors along the coordinate axis. Now, a singular n-simplex in a topological space X will be any continuous function from the standard n-simplex to X. As an example in this image, we have a 3 simplex sigma in the space X. From the singular n-simplexes, we define the group of singular n-chains as the free abelian group Cnx with bases consisting of all the singular n-simplexes in the space X. Its elements will be the formal sums of n-simplex as it's shown in the slide. Once defined the groups of singular n-chains, we have the boundary homomorphism between the group Cnx and Cn-1x, which takes each singular n-simplex to the alternating sum of each of its restrictions to a face of the standard simplex, which will belong to n-1x, since it's a sum of singular n-1 simplexes in X, and therefore it is well defined. With this, we have a chain complex between the singular chain groups, and we can define the n-th singular homology group as the quotient of the kernel of the n-boundary homomorphism by the image of the n plus 1 boundary homomorphism. An important result about homology groups is their homotopy invariance, that is, if two spaces are homotopy equivalent, then their homology groups are isomorphic for all n. This is an interesting result coming back to the question of comparing spaces, because if two spaces have homology groups that are not isomorphic, they cannot be homotopy equivalent, and consequently neither homeomorphic. It's not always easy to compute singular homology groups, as the singular chain groups may have an infinite basis of singular simplexes. An important tool for the calculation of singular homology groups is the Meyer-Vietore sequence. Given two subspaces A and B of a topological space X such that X is the union of the interiors of A and B, then we have the long exact sequence shown in the slide. This sequence is useful since we can take two subspaces of X's with homology groups already known in order to calculate the homology group of X. An example of this is in the calculation of the homology group of the Klein bottle, which can be computed by taking as subspaces two Möbius strips that are homotopy equivalent to circles, and the homology groups of circles are well known, as you can see the decomposition of the Klein bottle into two Möbius strips in the image. We will now discuss some applications of singular homology showing the versatility of this mathematical tool. The first result is the Harry-Ball theorem, which says that an n-sphere Sn has a continuous field of non-zero tangent vectors if and only if its dimension n is odd. The proof uses the idea of the degree of an application f of x Sn into itself, which depends on the homology groups of Sn. In the slide, it is possible to see that in S2, the vector field cannot be continuous because there is a point where the tangent vectors cancels out, forming some kind of swirl at the top of the sphere, hence the name hairy sphere for the theorem. The next result is the Brouwer's fixed point theorem in its n-dimensional version. The fixed point theorem states that for every continuous function f of the n-dimensional closed disk to itself has at least one fixed point. Generally, this is a result which is proved in analysis, but in its one-dimensional version. It will be a corollary of the fact that there is no retraction of dn in Sn-1, which is demonstrated using properties of the sphere's singular homology group. Another interesting application is in the proof of the Borsuk-Ulam theorem, in the n-dimensional version. The Borsuk-Ulam theorem says that every map of Sn in Rn has a point x in Sn such that the image of x is equal to its antipode in the Sn sphere. As an example, taking an embedding of S1 on the Earth's surface, we have that the function that takes a point S1 to its temperature is a continuous function of S1 on the real line, so there must be two opposite points on the Earth's surface that have the same temperature as it's shown in the video. Another result is the Jordan-Brouwer separation theorem, which is an analogous to the Jordan's curve theorem but restricted to the sphere Sn. It states that a sphere Sn-1 embedded in Sn divides Sn into two components, and the embedding is the border of both of them. The image illustrates the result for the case in which S1 divides S2 into two components. Finally, we'll deal with an important topological invariant, which is the Euler characteristic. The Euler characteristic of a topological space is defined in spaces with finitely generated homology groups. This may seem like a very restricted case of the theory, but there is still a very wide range of spaces that satisfy this condition. For example, every topological manifold has finitely generated singular homology groups. The Euler characteristic of a space X is defined from its Betti numbers, which are the rank of each homology group of X, considering only the infinite groups. The Euler's characteristic will be the alternating sum of Betti numbers, and as it depends on the singular homology groups of the space, it will also be a topological invariant. In addition, considering compact surface, it is a complete topological invariant because by the important compact surface classification theorem, every compact surface is homeomorphic to a sphere, a connected sum of n-tori, or a connected sum of projective n-planes. With that, knowing if the compact surface is orientable or not, we can easily classify it based on its Euler characteristic, as it will always fall in one of the cases in the table. Well, these are the main references for this work. We would like to thank CNPq, Conselho Nacional de Pesquisa e Desenvolvimento, for financing the project. Here is my contact email for eventual questions about the work, and thank you so much for your presence and patience.